Hello and welcome to Young Minds vs. Physics. This channel is meant to train you or help you in scoring better rank, whether you are appearing for IIT, JEE, or NEET, or boards, or KVPY, and so on. Right, today we are going to discuss about the effect of electric field on a point charge and a dipole. So here we are going to discuss about uniform and non-uniform fields. Right, as you see in the screen, we can see in the first case, right? So like a point charge, positive charge, like when it is left free to move in an uniform field, and you can see that the field is directed like from positive to negative plate, and if the positive charge is left to free to move left, and then it is repelled by positive charge and attracted by negative charge, thus it moves towards the negative plate, whereas the negative charge moves from negative plate to the positive plate. Right? That means you can easily say that the motion of positive charge is in the direction of the field. The motion of the positive charge is in the direction of the field. Like whenever the direction of motion is parallel to the field. Right? We say that it is direction of the motion parallel to the field, and a negative charge moves opposite to the field, right? Opposite to the field direction. And now look at the second figure on the screen. It's very, very important. You can see that the charges are thrown perpendicular to the field direction, or rather we can say that the charges are projected perpendicular to the field direction. Here you have a negative point charge and positive point charges, right? So now let us take the case of positive point charge or a positive charge, which is projected perpendicular to the uniform field here. Like you have that from positive to negative plate, right? So it is in the upward direction. Now suppose if you take the arrow marks to be along the y-axis and the projection direction along x-axis, right? You can see that the positive charge is taking again the path of a parabola. That means it is influenced by the electric field, right? And now when you see the negative charge, right, this also takes the path of the parabola, but how is it? Like it is moving towards the positive plate, right, in the parabolic path, right? And here the positive charge is moving towards negative plate, right, in parabolic path. So you can see like it is something like a horizontal projectile, like means a body which is projected horizontally in Earth's gravitational field. So in which path the body moves, in a similar manner you can see like these two cases. Okay, so this is about like motion of or the effect of electric field, the effect of electric field on charges, right? So anyhow we are going to see the mathematical interpretation of the concept just after the slideshow. And please do subscribe, like, subscribe, comment and share, and help us deliver more videos, upload more videos, and help thousands of students. And please do subscribe, share with your friends, and comment. Now this is about the dipole, right? If the dipole is in uniform electric field, look at the first figure, right? The first figure on the screen. So it is a dipole, right, with minus q and plus q being separated by a distance of 2r. Right, so now you have already seen that positive charge always tend to move in the direction of the field, and the negative charge always tend to move in the direction opposite to the field. And here the field direction is along y-axis. If we suppose E, right? Then plus q is having a force along y direction, and minus q is experiencing a force along negative y direction, opposite to the field. That means on the dipole at the two extreme ends where the charges are located, there two equal and opposite forces are acting. That means whenever a body experiences two equal and opposite forces at two different points, then it experiences, we say that it experiences a rotation, or it is having some couple, or rather we call it also as torque. So thus, if a dipole is left freely in the electric field, it experiences a torque, right? And that torque, you can see it here, and this is like it is now trying to tend to move in anti-clockwise direction. Quite good. And now observe the second figure. When it is a second figure, that means the dipole is in non-uniform electric field. In the previous figure, you have seen it is in uniform electric field. So therefore, you have plus QE and minus QE are the forces which are equal and opposite. And here, when it is non-uniform electric field, you can see that at one place it could be QE1, at the other place it is QE2, right? And always you can see that if the field is directed along the positive y direction, right? So the force on the dipole at one end is in positive y direction, at the other end is in the negative y direction. That means here the dipole will be pulled towards a stronger field, because here the field is not uniform. So that always the motion of the dipole will be towards, its alignment will be towards, its orientation will be towards a stronger field. Hold on for a moment and we will go for the mathematical interpretation just now. Now let us see the mathematical approach, right, of force acting in electric field on a point charge as well as on a dipole, and let us discuss it under both the conditions, right, for like uniform and non-uniform fields. Alright, see now if there is a point charge placed in an electric field created by so and so, suppose a charge of Q. That means what you have to imagine is an electric field created by capital Q. In this electric field, now at this point, if the electric field strength is E, imagine or put a charge small q. Suppose if there is a small q which is left free. Right now what happens? There will be a force on this. Of course, you know that very well. It is Coulomb's inverse square law only. That is 1 by 4 pi epsilon naught q into q by r square. Right? So the same here we are writing it as E. What is E? Electric field strength is 1 by 4 pi epsilon naught q by r square is E into q. Right? So this is ultimately understanding Coulomb's inverse square law and the relation between F and E. That's all. Okay. This is when this is in some electric field. Now suppose if it is left in a non-uniform electric field. Okay, right? So this is electric field only because of a single charge, single point charge, and you are doing it, right? So suppose if it is in uniform electric field as we have seen in the slide, right? Plus being the charge of this one, that is a positive plate and a negative plate, and you know that the lines of force always emanate away from the positive charge and move towards the negative charge, and this is how the field is. Now if you are leaving a positive charge, what happens here? This moves in the direction of the field, and a negative charge if you leave, this moves in the direction opposite to the field. This is what we have seen. Now if it is a non-uniform field, right? Let us suppose you have a dipole. Very good, you have a dipole, right? So how the dipole lines of force, this is how the lines of force of a dipole. Right, that means definitely this is a non-uniform field, right? This is a non-uniform field around the dipole. So in this field, right, in this field, if you leave a charge here, a point charge Q, suppose, so what will happen? Yes, what will happen? You know pretty well, right? So at this point, suppose if it is positive charge, it is repelled by this and this is attracted by this, and therefore this is how it moves. And we have determined E at this point because of the dipole. Of course, the field around the dipole is non-uniform. Now if you leave a charge at this point, now find out the effective E at this point, and then F is equal to EQ. Fantastic, that's all. That means always whenever like only a point charge is moving or whenever a point charge is left free to move, what ultimately you have to find is like whether it is uniform field, non-uniform field, whatever it is, you find electric field strength at that point. That's all. Multiply the electric field strength with charge which you are putting there. Finished. Okay, F is equal to EQ. So this is very simple, right? So it's not so complex. Only the thought when you think of it like, yeah, I know only uniform charge, I don't know. I know only Coulomb's law, I don't know this one. Nothing to be worried like that, right? So always F is equal to EQ is the force experienced by a point charge which is left inside the field. Right, the field may be uniform or non-uniform. What the only thing is, at the point where you are leaving the charge, find the effective electric field strength at that point, and happily you can determine the force acting on it by F is equal to EQ. Right, done? Clear? Yes. But theoretically you should know how and where the charge would be moving. Right, that means what will be the acceleration of the charge? What is acceleration of the charge? So A is equal to EQ by M. So this is the acceleration of the charge. Right, once when you know the acceleration of the charge, when you are leaving it like at rest, you can also calculate all other things using all your kinematic principles. Right, using V is equal to U plus AT, S is equal to UT plus half AT square, and all those equations of motion can be used here again. So ultimately what you should know to know the effect of electric field strength on a charge means at that point you have to determine electric field strength. That is very, very important. Okay, yes, and as well as when you know the magnitude, you should also know the direction. Right, so that is how you have to determine it. Now coming to a dipole now, right? So dipole is not a point charge, is it not? Dipole is not a point charge. It is something like two charges of equal magnitude but opposite signs are separated by a fixed distance. That means it is something like in a field, it is something like two charges being combined, and now how does it move? If one charge is moving, you will write F is equal to UQ and finalize that in which direction the charge is moving and all that. But it is here, it is something like a body, which is having a positive charge on one end and negative charge on the other end. And one end may be at one particular field and the other end may be at another particular field, if at all dipole is in non-uniform field. And if it is in uniform field, so therefore dipole has to be studied in a different manner in uniform field and non-uniform field. So I will separate this as like now, like on a dipole, what will be the effect of the field strength? What happens to the dipole when it is left free to move in a uniform field? First we will see uniform field. Right, so now let us see that this is uniform field. As always, the uniform field is represented by parallel lines, parallel straight lines. Right, so now let this be E bar. Right, our magnitude of this is E. Now a dipole is like this, like aligned by making an angle of phi. Right, that means the length of the dipole is making an angle phi with the field lines. Right, so this is phi. Now if the dipole is this and 2L is the length of the dipole, and you know that P bar, that is a dipole moment, always acts from negative charge to the positive charge of the dipole. This is very, very important whenever you solve problems. Right. So these are all the things which are given. Now we have to make the case study. Here positive charge is here. Now we are not bothered about any other thing. Now there is a positive charge here. How much force is acting on this? Right, already we studied just now on a charge in the electric field. Always if the charge is positive, the force will be in the direction of the field, right? So now here there is a positive charge left, and now here is the direction of the electric field. So therefore in that direction there will be a force acting on the charge which is equal to electric field strength at that point multiplied by the charge. So E bar Q is F plus bar. On positive charge I am writing it as F plus bar. Now take this one. Already we studied just now, right? On the negative charge the force will be opposite to the electric field strength, right? That means here this is how it moves, right? It moves away from the positive charge, or it moves anti-parallel to, the force will be acting anti-parallel to electric field, right? So therefore this is how it is. Now the magnitude is again EQ here and EQ here, right? Magnitude is same, and then now when it comes to the directions, they are opposite. So what is happening? Already in the slideshow we discussed about this. When two equal and opposite charges are acting on a body at two different points, then the body tend to move. Right now the body automatically moves, and that movement is a rotatory movement. Right? So when the body is brought into rotation, then when two equal forces are acting at two different points, we call that it experiences a couple or torque. Right? And the torque and the couple are given by force into perpendicular distance, that you know very well. Now our point is to find out the perpendicular distance between the two forces. Right, one force here and the other force here. This is the perpendicular distance. That means this makes 90 degrees here. So this is a right angled triangle. So in this right angle triangle, hypotenuse is 2L. Now opposite side is 2L sine phi. So we know the perpendicular distance now. 2L sine phi is the perpendicular distance. Therefore, couple or torque is equal to force into perpendicular distance. Magnitude of each force is EQ. So EQ into 2L sine phi, where Q into 2L is dipole moment. Charge into length of the dipole is dipole moment. So therefore you will replace it as EP sine phi, and in the vector notation we will write it as toe bar is equal to P bar cross E bar. So toe bar is equal to P bar cross E bar. So now we can see that, right? We can see that always the electric field tries to pull the dipole in such a manner that its dipole moment lies in the direction of the field, right? So it shows its effect in such a manner that the dipole should be aligned parallel to the field lines. So this is how the field will be influencing the dipole. So in this process, the dipole experiences a couple, and then it rotates, and then it comes and try to align parallel to the electric field strength. Okay, this kind of concept you will be seeing in magnetism also. Like when you leave, like what do we say, freely suspended magnet, right? It tries to come to rest in the direction of the Earth's magnetic field, is it not? So in whichever direction you are leaving it free to move, it experiences a couple and then rotates and then comes finally to rest in direction of the magnetic field. In a similar manner, the field always tries to make the dipole align parallel to its direction, right? Very good. Now when you observe this one, sine phi, which shows that when phi is equal to 90 degrees, tau is maximum. That means when the dipole, right, when the dipole is perpendicular to, right, this is my field. I am taking this as my dipole. If the dipole is perpendicular to the field strength, the torque experienced is always maximum. The torque experienced is always maximum. When the dipole is either parallel or anti-parallel. Parallel or anti-parallel. I took both the conditions. One plus minus condition, one minus plus condition. That means when the dipole is anti-parallel, how are we taking the direction of it? Depending on P bar. Depending on P bar. So E bar, it is in this direction. P bar is always from negative to positive charge of the dipole. That is very, very important. You have to remember. So when P bar is parallel to E bar, that means phi is 0. Right? You can observe the diagram here. So P bar is making an angle of phi with E bar. Now when this is 0, that means P bar and E bar are collinear now. Right? So then the couple is 0. Or else if P bar is anti-parallel, that means when the dipole is absolutely aligned like this, right? Even at that moment, the couple or torque experienced is 0. That is minimum. Clear? Right. So please pause for a moment and note it down. So as immediately as you note down the points, important points, while you are listening, that is going to help you a lot. So that will be recorded at two places, one in your mind and the other in your book. Right. So now let us move to non-uniform field. Okay. So when it comes to non-uniform field, let us suppose that there is a dipole, right, where the dipole moment is in this direction, that is along the positive x direction. Right. Now here this is how the field is non-uniform. Right, and the direction is somehow in positive x direction like this here. Now since it is positive, so to the direction of the electric field, it is experiencing FB in this direction. And this is minus charge, therefore FA in opposite direction. So why are we writing it as FB and FA? Means because here the electric field strength is different. Here the electric field strength is different. At 2 points A and B, electric field strength is different, but because we have imagined non-uniform field, right? We took non-uniform field. Therefore, field strength is not the same at every point. So it is different. It is different. The magnitude is different and directions are also changing, and we are taking in this direction where the field line is going like this. Suppose if the field line is going like this, so this is the direction in which you have taken the dipole, right? And here the magnitude of electric field strength is EA, and here the electric field strength is EB. Right? So therefore, you will be writing it as F is equal to QEA and this is QEB. Right? So now what is the net force acting on them? Right? Both are in opposite directions. Therefore, F is equal to FA minus FB is QEA minus QEB, or Q taken out and it is Q into EA minus EB. Now, how is this changing? Right? There is a change. There is a continuous change. Suppose whatever the change that is taking in this direction. Right? That means EA minus EB, in the sense there is a difference in the electric field strength. Right? If that is a continuous electric difference, then you say that it is DEA. Is it not? So DE. Right? So now you have that as delta E or DE, you can write it. And for our convenience, how it is changing? It is changing along the length of the dipole. Right? It is changing along the length of the dipole. So that means the change per unit length you have to measure. You have to measure change per unit length. Change in electric field strength per unit length of the dipole. That means the dipole is not focused at a point. It is stretched. It is stretched at for a length of 2L. Right? So therefore, the electric field surrounding it, the electric field here it is changing. How it is changing? We need to find out how it is changing with respect to the length of the dipole. So I need dE by dL or dE by dx. Therefore, I just wanted to multiply 2L to this and to divide and multiply this with 2L. So Q into 2L is dipole moment, which is a constant to a given dipole. It is not going to get affected by electric field strength. So therefore, we take this as
P as it is. So now P into EA minus EB by 2L, that is delta E by delta L, or you can write F bar is equal to P into dE bar by dx, and modulus of F bar is equal to modulus of P into dE bar by dx. So what is this dE bar by dx? dE bar by dx is called the gradient of the field in x direction. Here it is in the x direction. So instead of dl, what we are taking in x, because the electric field strength is changing in this direction. So therefore it is dE by dx is a gradient of electric field in x direction. Now you know this beautiful concept can be understood like we can interpret this one with electric induction, and when suppose if you are charging a body like a comb, you are charging it by rubbing it with some fur or something, and then when you take the comb near the paper, bits of paper, here we didn't do anything to the bits of paper. Bits of paper are neutral. We did not charge them, right? But the comb is charged. So when this charged comb is taken near to the bits of paper, you observe that they will come and cling to the comb. Right? Why is it happening? Why is it happening? See, suppose if you have a comb here, right? Alright. And now you have bits of paper, right? And these are going and sticking to this. Why is it happening? Why is it happening? Because of the comb, there is some non-uniform field created here. And it is very brought near to the papers, therefore there is an induction taking place here. When it is an induction, you will have positive and negative both. That means suppose if all the electrons move to this end, free electrons move to this end, then this area is deprived of negative electrons. So therefore it will become positive. So that means this will now act as a dipole. So this paper strip will act as a dipole. So what happens? This dipole is getting attracted by this, right? And thus it is moving from, now where is this dipole? This dipole is at a weak field. This is at a weak field. Now when it is going, like means when we move from this to this distance, that means along this distance if you move, right, the strength keeps on increases as you are moving closer to the comb, right? So therefore what is happening? This dipole is pulled towards stronger field. This dipole is pulled towards stronger field, right? So thus this whatever you have studied here, this dE by dx, that is the gradient, right? Electric field gradient, right? This makes the dipole move from weak fields to stronger fields. Beautiful, is it not? Yes. So when you take this as a concept, and if you try to understand and interpret whatever mathematical concept is there with the theory what you have already studied, so then that creates interest in solving problems. Okay, please note it down. Pause for a moment and note it down. Yeah, here is an example. So we are taking in order that you understand how the non-uniform field is going to affect a dipole, right? Right, or influence a dipole. So here is a problem. Right, this is from Cengage physics. So this example definitely clears if there is any kind of ambiguity or confusion in your mind, right? So like in a certain region of space, there is electric field along z direction, and the magnitude of electric field is however not constant. Of course the direction is constant, but magnitude is not constant. Thus without any doubt you can take always the electric field being acting in positive z direction. Pakka, fixed. Right. Now at the rate of 10 power 5 Newton per Coulomb per meter. That means here what is given? What is given to us as we are reading the problem, we should understand. dE by dz is given to be 10 power 5 Newton per Coulomb per meter. Right. So this is what which is given. Or rather we can write it as a Newton Coulomb inverse meter inverse. Right. So now dE by dz is given here in the problem. That means how the electric field strength in the z direction is changing. That means electric field gradient is given in this direction. What are the force and torque experienced by a system having a total dipole moment equal to 10 power minus 7 Coulomb meter? So what else is given? Dipole moment is given. So P is given, or modulus of P bar, which is 10 power minus 7 Coulomb meter is given to us. Right? And how is this given? This direction, this is in negative z direction. Beautiful. So no other angle is given. Already negative z direction means dipole moment is in negative z direction. E is in positive z direction. So what is phi is equal to 180 degrees. Clear? So what is the question asked here? You have to find the force and torque. Now torque here is equal to whatever it is, uniform field, non-uniform field, whatever you take here, phi is equal to 180 degrees. So torque toe bar is equal to, you know that it is P bar cross E bar. Where that is equal to PE sine 180, sine 180 is 0, therefore 0. Done. Finished. So easy to understand here. Right. Now the point here is to find out F. What is F? Just now we have seen F is equal to P into dE by dz. Right. P into dE by dz. Now you see, like, what is happening? Right, from the diagram, from this thing also you can draw the diagram here. The P is in this direction, dE by dz in this direction. Right, so directly you can write that. Means suppose if the electric field strength is E here, so by dz distance, it should be E plus dE. So you can imagine it to be dz distance and you can find out the net force. Or directly, don't go for all that directly, because we have learnt just now what is the force that is acting on the dipole because of a non-uniform field, that we learnt it. So there is no need for us to confuse with all other things, right? Now you do it. Now what is P? 10 power minus 7 into dE by dz is 10 power 5, which is equal to 10 power minus 2, right? And this is newtons. So finished. Is it not? Yes. One. And if you have not yet subscribed, please subscribe. And also I would like to thank all the subscribers who have put your trust in me, and definitely so I'm going to help you in scoring a better rank. Thank you.